All right, we are going to do 3.3, which is the factor theorem and the remainder theorem. So the factor theorem is very, very important. And what makes the factor theorem a little bit difficult is that there are three different parts into play. So I am just going to make this a continuous graph. There we are. The factor theorem, x minus a is a factor of p of x if and only if the p of a is equal to 0. Suppose we have a polynomial. Now I'm going to make this a function. Suppose that that y is equal to p of x is a polynomial function. The factor theorem is x minus a is a factor of p of x if and only if p of a is equal to 0. Well, just to pick this apart a little bit here, I'm going to try to share three pieces. You can say this looks like a lot of the remainder theorem. Great. So another way to say this, or to look at this, x minus a is a factor of p of x if our remainder, using the remainder theorem, is 0. Makes sense. I hope. That's all it's saying. So now I'm just going to pick this apart a little bit differently. Now this is a theorem and it is a double implication, we call it. That is, you could read it forwards and backwards and it's still true. X minus a is a factor of p of x if p of a is equal to 0. So when you take the remainder theorem and you consider the factor x minus a, if the remainder is 0, then x minus a is a factor. Or, now I'm going to interpret this a little bit differently later, or if the remainder is 0, then x minus a is a factor. So you could either say x minus a is a factor of p of x if p of a is equal to 0, and if p of a is equal to 0, then x minus a must be a factor. So that is a very, very strong statement. So it is bidirectional. So in the context of this question here, I apologize, in the context of this question here, if p of x is equal to 0. Now, if p of x is a graph, I'm just going to pinpoint 2 points. Did you guys know that the p of -1 is going to be 0? So that's what it looks like on the graph. For instance, when we have an x-intercept, we can conclude that there's a corresponding factor that exists. Now later on we can easily construct the equation of this polynomial, but now let's take a look at this. What we're saying is this is the p of this is the p of positive 2. The p of 2 is equal to 0. Right? And the reason why this is so hard is because now I switch to a function. Now, there is a connection between the function and the factor theorem, and the p of 2 is equal to 0, so that implies that x minus 2 is a factor. All right. So we're good. There's the factor theorem. So here's me just playing. I think that we understand that if x minus a is a factor, we can use the remainder theorem, essentially. And if our remainder is 0, then x minus a is a factor. X minus a is a factor, then, if p of a is equal to 0, then x minus a is a factor. All right. I know to some of you that might mean the same thing, but here we're almost saying, like, if we have a chihuahua, it's a dog. And if we have a dog, it must be a chihuahua, right? It's kind of weird. I get it. Anyways, let's just start off with a nice, cute example here. Let us consider y is equal to x squared plus 3x plus 2. Now this is great. You may sketch this out. It's an upward opening parabola. Some of you guys are going to do this. So I'm just maybe trying to demonstrate the factor theorem just a little bit more. If I factor it into this, essentially, what do we know? We know that when I factor this, I will have a 0 of the function, right? I will have the 0 of the function, or an x-intercept at -2. And, sorry, I made a mistake. I will also have an x-intercept at -1. All right. So far, so good. Also, if I'm giving the x-intercepts, I can create the factors, then create my function. All right. Enough of this. Let's move on. Really, it's the remainder theorem wrapped up in a special way. That's what the factor theorem says. So the integral 0 theorem, if x minus a is a factor of a polynomial, that is, if we have a factor x minus a of polynomial p of x, then a is a factor of the constant term. All right. We use the 0 integral theorem to begin the factoring process. So, if x minus a is a factor, then a, so this a corresponds to this a, we're talking about the same a. If x minus a is a factor of the polynomial p of x, then a is a factor of the constant term. So, really, here's my constant term. I'm looking for possible factors to start factoring this completely, right? What are some possible factors? Good, I don't know either. But I can use this theorem to say, well, what are the factors of my constant term? My constant is -2. So the factors of this, of -2, are plus or minus 1, plus or minus 2. So here, maybe I should switch colors. -1, 1. And switch it to -2. Oh, ran out of colors. And +2. These are my factors of my constants. So, what is a potential factor when a is -1? Well, for the red, it would be x plus 1, because the potential factor is x minus a. If a is equal to 1, corresponding potential factor is x minus a. If a is equal to -2, the potential factor is x plus 2. If a is equal to +2, the potential factor then is x minus 2. Which one of these are factors? Perhaps all. I'm not too sure. I wish there was something called like the factor theorem or something to basically help me to decide which one of these are factors. Ah, that's right. We have to look for our P of A's, right? We need to look for which P of A's are equal to 0. All right. So I'm going to stop the video right now, and then I am going to actually answer the question. Now let's take a look what the question said. I was just trying to understand this integral factor theorem. Now let us do the question, and we're going to factor this completely. Stay tuned for the next video. I'm sure it's going to be way more exciting than this one. No promises though.